Hi. Thanks very much for your interest on this topic about enabling indoor positioning using ubiquitous inertial sensors and Wi-Fi FTM rangings with an extra dynamical calibration mechanism. Context will be briefly clarified, and then it will go through the implementation together with a demo video. At last, some analysis on the experiment results will be discussed. Indoor positioning usually demands higher accuracy use cases, and not any single dominant solution has been accepted as the outdoor counterpart. In this work, it takes advantage of the emerging high-accuracy Wi-Fi FTM ranging technology together with ubiquitous inertial sensors to achieve the indoor positioning and prove the feasibility. The first component is pedestrian dead reckoning, which uses inertial sensors as the source input data. It tracks users' relative position upon the initial location continuously, by accumulating the estimated step length and heading direction at each step. However, due to the fact that the noise of sensors is also accumulated along with the estimations in each step, the estimated trajectory of the user has a drifting effect which will be further and further away from the actual route. The other component is known as FTM ranging, which is able to accurately measure the distance from a certain Wi-Fi access point towards the device. Through straightforward geometric processes, that requires at least 3 reference access points with their exact location coordinates provided beforehand, users' position could be found using methodologies such as trilateration. The skeleton framework of this system is extended Kalman filtering, fusing the source data from PDR and Wi-Fi FTM ranging measurements. Besides, there is an extra dynamical Wi-Fi FTM ranging calibration mechanism associated to help obtain the up-to-date and reliable calibrated ranging measurements. Prediction phase of the Kalman filtering relies on input from PDR algorithm that tells information about step length and orientation. For measurement update phase, 2 implementations were conducted for comparison. Namely, to perform trilateration first, or row rangings directly. And a simple one-order polynomial was applied as the ranging calibration model. Here is a screen record of the demo application which intuitively illustrates how the positioning was going on. Dashed circles are the rangings from each access point. Green trajectory is the output of PDR and orange is Wi-Fi ranging trilateration only. Purple is the ultimate fusion result. To evaluate the performance of a solution, a test routine was designed, which forms a repeated H-shaped route. The test area is about 676 square meters, that is enclosed by 10 access points that were deployed around. 4 configurations were compared in order to highlight the fusion and calibration effectiveness. There are trilateration only, PDR fused with trilateration, PDR fused with row ranging, and PDR fused with calibrated ranging respectively. Through the CDF curves, it is observed that with help of fusion with the inertial PDR algorithm, accuracy increases significantly against FTM trilateration alone, even with longer FTM interval. And with FTM ranging calibration activated, accuracy reached 1.5 meters at 70 percentile. Dense access points deployment obviously helps keep higher accuracy of the positioning result. However, with access points density in this case below 112 square meters, the accuracy improvement will become much less observable. Access points allocation strategy effects on the accuracy cannot be neglected as well. Experiments showed that the worst case was caused by the case where all access points were in line, which is unfriendly towards trilateration. On the contrary, wider coverage of the AP deployment helped keep robust and reliable results. Non-line of sight conditions of access points are commonly seen in actual scenarios, which decreases the accuracy if too many NLOS APs were involved, according to the experiment observations. This work explores the feasibility using EKF using the PDR and Wi-Fi FTM rangings to achieve indoor positioning, through a series of experiments and analysis. Access points deployment strategy and NLOS effects were discussed for future reference. With frequent FTM sampling, the fusion result can reach 1.5 meters that satisfies many indoor use cases. Thank you for your interest on this topic.